So we're continuing on with filling in our table for Laplace transforms. And at some points we have to say, look, we can't get every possible function, so we're going to get the highlights. To an extent, this is mostly the highlights of the functions. We're going to add one more to the list on the left-hand side, but not today. We've got to save something for Wednesday. Today, we're adding this block that you see marked off as today. So that's sort of the clue as what we're doing today. And so the nice thing is it's sort of, there's a theme going on, which says, hey, when I looked at taking the derivative, it essentially resulted in multiplying by s. So when I start with f prime of t on the one side, I get s, f of s on the other side. Well, there's a little bit of a correction there. So it's like, all right, so if derivative corresponds to multiplying by s, well, what's the opposite of multiplying by s? Divide by s. What's the opposite of derivative? Integral or antiderivative. And that's the first thing. The antiderivative corresponds to dividing by s. Okay, so that's not a big surprise. We'll go through the justification. Now, there's a little bit more than antiderivative there, but we'll talk about that. But the more interesting thing says, hey, we start with the derivative on sort of the input. We can also talk about the derivative of the output. So it turns out the derivative of the output corresponds to multiplying by t in the input. Very similar. And of course, if we can multiply by t once, we can multiply by t many times. And from that, we can get things like t times sine, t times cosine. And then the last thing says, what about multiplication? And the answer is, ooh, that's interesting. A little bit different than what you think, because that's not what you're thinking when you think multiplication. But we'll get to that towards the end. So let's start at the top. We'll work our way down. All right. So our goal is to say, all right, we're going to look at a function, g of t, which we create by saying do the integral from 0 to t of f of tau d tau. And then we're going to find what's the Laplace transform of that. So that's our goal. Now, before we get into it, we actually have two different proofs we'll go through. We've already said this. We're going to say it again just so we understand. This is the antiderivative of f of t. That's what we're really talking about. Now, it's not just any antiderivative of f of t. It's a very specific antiderivative. In particular, what can we say about g at time 0? It's 0. Okay. Now why? Integral from 0 to 0. Well, integral 0 to 0 of anything is nothing, because you don't have any time to accumulate. There's no accumulation that can occur if you start and stop at the same point. So that's one of our basic facts. So the real moral here is, what's the antiderivative? What does that do with the Laplace transform? That's what's going on here. Well, there's two ideas. They're closely related to each other. One is to say, hey, we've already invested time. Let's not reinvent everything. Let's use the tools we have. And the tool we have is we know how to take derivatives. So we'll start by saying, all right, we know what the Laplace transform of just a function is. We'll call that capital F of s. And now we say, well, what's the relationship between our function f and our function g? Well, we have that our function g is the antiderivative of f. So this is the Laplace transform of g prime. This is what we mean by saying g is the antiderivative of f. So g prime equals f. And now we say, all right, how do you take the Laplace transform of a derivative? The answer is, we grab our chart. If I want to take the Laplace transform of a derivative, it's s times the Laplace transform of the function, subtract the function at 0. So that's where we get the s times g of s, subtract g of 0. But what do we know about g of 0? It's 0. So it's just s times g of s. And finally, the magical trick called divide. So g of s equals f of s over s, and we're done. That's the proof. Perfectly valid. Now, the other way we can do it is we can say, hey, let's recall how we proved the derivative rule and just repeat the same idea. And we did that by using integration by parts. So we say, all right, we're taking the Laplace transform of g. So that's the definition of how we take the Laplace transform of g. And now we say, well, previously we took the derivative of we were going to take the derivative of the e to the minus st part. Now we're going to do the opposite, which is we're going to integrate the e to the minus st part and take the derivative of the g part. So we're doing integration by parts. So derivative of g, that's f. So that's where you see the derivative of g is f. So that's where the f comes in. The antiderivative of e to the minus st, and remember, we're talking about with respect to t, it's e to the minus st, and then you have to account for the constant of minus s upstairs. So you divide by minus s. So that's where the minus 1 over s is coming from. So we have uv minus v du. But we say, hey, we know what happens at infinity. At infinity, the e to the minus st term drives the expression to 0. We know what happens at 0. G of 0 is 0. So the first term goes away. Then you have a minus, so that's where you get rid of the minus. 1 over s can come out. 1 over s, the integral, 0 to infinity, e to the minus st f of t dt. And we're like, wow, we recognize that. That's the Laplace transform of f. So we get f of s over s. And same result. All right, good. So let's do an example. Find the inverse Laplace transform 1 over s times s minus 3. Now before we start doing that, if we hadn't just had our discussion right now, what would we think of doing? Partial fractions. Does partial fractions work on this? Yes. And is there anything wrong with partial fractions? No. To be honest with you, if I saw this problem while I was out walking and I said, ooh, I see that problem, I would say, that looks like a partial fractions problem to me. So if you look at this and say, hey, I'd still want to do partial fractions, that's okay. That's all right. The moral here is to show you there's alternatives. See, we're getting to the point in mathematics where there's not just like you have to do exactly this and there's no other option. We're showing you there are options. And that can be good or bad. And so just be comfortable with what you can do and make sure you know enough. So if the following you don't like, you don't have to do it. You could have done partial fractions. So what's the idea? Well, the idea here is you look at this and say, this has the form of f of s over s. The over s is because of that s there, where the f of s is 1 over s minus 3. Okay. Now, if f of s is 1 over s minus 3, this corresponds to a particular function f of t. So this is time for us to go back to our table. What does 1 over s minus 3 correspond with? Can we see anything? Yeah, so that fills the form here, 1 over s minus a number. That's e to something t. In our case, something is 3. So that's e to the 3t. So now what we do is we say, our great aha, what must be the case is that we want to find the antiderivative. So that's what we're after for the answer. Because if you have f of s over s, that comes from taking the antiderivative. Well, not just any antiderivative. In particular, we can say it's the integral 0 up to t of this function, e to the 3 tau d tau. If you don't like this, just find the antiderivative and find the right constant. But let's go through and use the formula as written. What is this integral? So 1/3 e to the 3 tau, evaluated from 0 to t. When you plug in t, what do we get? 1/3 e to the 3t. When we plug in 0, what do we get? 1/3, because e to the 0 is 0. And now, what comes next? Someone said box. That's right. That's the answer. That is the correct answer. So you might say, wait, did we really do it? So we found the antiderivative, and really, if you're doing this by thinking about finding the antiderivative plus find c, is what happens here. If you go through and do partial fractions and carry out the whole step, you will see that this is indeed the right answer. It gets you the same thing. All right. So this is an alternative if you happen to have an s there. Now, if you have multiple s's, can you do this? And the answer is, well, yes. If you have multiple s's, what does that mean you need to do? For every s, what should you do? Integrate, yeah. So for every s, you do an integral, and you just keep doing it over and over and over again. At some point, you're like, forget it. I'll just do partial fractions. Okay, so coming back to our chart, we now say we have marked the first one, f of s over s. So the next one, this is a good one. I like this one. Okay. And it's a really cool idea. And here it goes. So we start by saying we're going to take the derivative of the transform. So we go to the definition. F of s, definition, integral 0 to infinity, e to the minus st f of t dt. And we want to talk about the derivative, f prime. So we do what we should naturally do, which is we're going to take the derivative. And that feels good. It feels actually pretty nice. So what happens? Well, so f prime of s is the derivative of this expression. And now we say, aha, where is the s? There's only one place s is showing up. S is only showing up in here. So what we do is we push the derivative inside. So the derivative pushes into the inside of the integral. So we get the derivative of e to the minus st. Now you might say, are we allowed to do that? It feels good to do that. And most engineers would say, if it feels good, it must be okay. In the meantime, mathematicians will spend 10 years verifying that it's actually good. And the answer is yes. You'll notice that there's a sort of parenthetical comment I didn't talk about. There are some issues about can we really push the derivative in? And what's happening is there's two limits involved. A derivative is a limit, but also an integral is a limit. And so the question is, well, can you swap limits? And you can under certain circumstances, and it turns out we are in the right circumstances, but we're not going to tell you the details. That takes a little bit of work. Another 2 semesters or so probably should be enough, but for now we'll just accept it. All right, well, we're basically there. When I take the derivative of e to the minus st, what happens? And remember, taking the derivative with respect to s.
The negative t comes to it's going to come out front.
The negative t comes out. It's an exponential function. Derivative of an exponential function is the exponential function. Again, you just have to remember to take care of the what's upstairs. Chain rule means that you need to bring a negative t down. And now the negative comes out in front of the integral, and the t comes and joins the f of t. And we look and say, aha, that's the minus sign. And then we're taking the transform of t times f of t. And that's the result. That's it. So every time we have a t that we have multiplying in, there's a minus that comes in, and there's a derivative. Well, so if I have a lot of t's, t to a high power, well, I have that many minuses, n minuses, and I need to take n derivatives. So now I can take t to any power times f of t. As long as I know what f of t is, I can go through and carry out this computation. Okay, so let's try an example. Find the Laplace transform of t sine of bt and the Laplace transform of t cosine bt. Now we haven't done these yet. We didn't have the good tools. So now we have good tools, so let's do it. So let's start by writing down what we know. So in terms of this problem, what do we know which is going to be useful? And I put up some formulas here. Which formulas do we want to grab? Well, certainly we want to use the fact that t times f of t, which these are things we proved. But what else? Yeah, the sine and cosine. Given that we know what sine and cosine do, now we can have, we can handle the extra t there. So for reference, we'll say the Laplace transform of sine is b over s squared plus b squared. And the Laplace transform of cosine, that's this one, s over s squared plus b squared. All right. So we have to do both. Let's start with sine. We saw the sine, and hopefully it'll open up our eyes. All right, so t sine of bt. So following the rule, I want to take the Laplace transform of t times f of t. It's the minus, so this minus will ultimately come over to here. So there's a minus, and then you take the derivative of just what would happen if you took the Laplace transform of the sine. So minus the derivative of b over s squared plus b squared. So there's our minus f prime of s. How do we take that derivative?
F prime g minus g prime f. And so your first term is just going to be 0. It's constant.
Okay. Someone suggesting quotient rule. Yeah, so quotient rule works great here. You can also avoid quotient rule if you like. If you think back to your old tricks that you learned from calculus, s squared plus b squared downstairs is s squared plus b squared to the minus 1 power. And now, well, the minus is there, the b is a constant. How do you take the derivative of s squared plus b squared to the minus 1 power? Someone's saying bring the power down, right? What rule is being used? Yeah, chain rule, chain rule's an awesome rule. It's the chain rule. Okay, then what happens? Well, there is a derivative on the inside, but before we get to the derivative on the inside, what comes next? You leave the inside alone, and then the exponent becomes minus 2. And then someone said derivative of the inside, that's the chain rule, so we multiply by 2s. So minus minus, those cancel. You have a b and a 2s, so that's 2 times s times b over s squared plus b squared squared. Because that minus 2 means that you're downstairs. And there we go. That's it. Cool. Well, similar idea for cosine, right? So Laplace transform t cosine bt minus the derivative of, in our case, it's s over s squared plus b squared. And I think this is a case where the quotient rule does make more sense. Okay, so now, do we remember the quotient rule? Yes, okay, that's a positive sign. How does it go? All right, someone said low D high. That sounds like a wonderful way to, very sing-songy way to remember things. Bottom times the derivative of the top. So bottom, s squared plus b squared, derivative of the top, 1, minus the top, s. Derivative of the bottom, 2s. And, of course, the bottom squared. All right, now let's clean this up. We have s squared minus 2s squared, which would be minus s squared, but then there's this extra minus in the front. So it becomes s squared. Then we have b squared, but there's a minus. So minus b squared all over s squared plus b squared squared. And there we go. And how did we do? Did we get it right? Well, there's our t sine bt. Oh, this said b times s. We have s times b. Oh yeah, they're the same. No problem. And s squared minus b squared. Yep, good. Woohoo, it works. It works. Ah, so nice. Okay. All right, good. We got a lot of our formulas already done. Okay, so let's try something with this. Use Laplace transforms to find a non-zero solution to t times x double prime plus t minus 2 x prime plus x equals 0 with x of 0 equals 0. Wow, this is good. Okay, now for reference, let's pull up our sheet of formulas here. And I want to point to these right here because we have x double prime and x prime involved. So just for our reference, x double prime, well, that's going to go to, according to this, s squared, all right, as x of s minus s x of 0 minus x prime of 0. And x prime, again copying from our sheet here, that's going to go to s x of s and minus x of 0. All right, so that's good. Now, can we simplify any of this? Yes, what can we simplify? Yeah, x of 0 equals 0. Okay, so those terms go away. And x prime of 0 is? We don't know. They didn't give it to us. They're cheating. Now, you might say, how are they cheating? Because Laplace transforms, you have to have initial value problems. And they didn't give us our initial values. Those punks. All right. Well, we'll deal with it when we have to deal with it. So but we'll just simplify it as this for the time being. Okay. So now let's get into the problem. The problem proper, as they say. First thing is, before we take Laplace transforms, I'm going to do a little bit of rewriting. Not much, just enough. Just enough. And at first, it will feel like we've done hardly anything at all. But what happened? What did we do? We expanded. Now you might say, why did we expand? Well, the reason is we know how to handle t times something, and we know how to handle a constant times something, but we really haven't talked about what to do with t minus 2. So by expanding, we're saying let's take it into parts that we know how to handle. It's a very common strategy. All right. Good. So now we have 4 pieces. Well, 5, but the 0 is super easy to take care of. So we're going to go through and talk about each one of these. What happens to tx double prime? What will this become? And if it helps, remember the rule. So t times something goes to minus the derivative. So this is what we would have if we just had x double prime. So what do we need to do? Take the derivative and don't forget the minus. Now, the reason I say don't forget the minus is when I did the other class today, I forgot the minus and it took me 15 minutes to figure out what happened, because it was very badly when you forget minuses. Minuses, grrr. Okay, all right, so here we go. We're going to get minus, what's the derivative of s squared times x of s? So what rule do we need? Product rule, okay. So we say derivative of the first is derivative of s squared is 2s. Leave the second alone. minus the first times the derivative of the second, that's x prime. And what's the derivative of x prime is 0? Well, it goes away, right? So even though they didn't give us x prime is 0, it's okay because it disappeared off into the ether. All right, how about the tx prime? What will that become?
Negative xs.
Negative, good. Product rule again. Derivative of the first would be 1 times x of s.
Minus s x prime of s.
Okay, and s, x prime of s. It will ultimately become a minus when we put the minus through. We'll get the minus there eventually. All right. Next term, the 2 minus 2x prime. What will that become? Well, minus 2 is minus 2. Transform of x prime? S, x of s. It's right there. Okay, and finally, the last part, we have the x. Well, that's x. Well, I shouldn't say finally. All that equals 0. Okay. Whew. That's a lot. Going forward, I'm going to now stop writing x of s, that capital X of s, and just say capital X. So what do we do now?
Is this another JP2 problem?
Is this a what?
Now we have x's and s's, and then we have x primes. Now we have to figure out what x is.
We do have to figure out what capital X is.
This is a differential problem from earlier in the semester.
Whoa! Someone is connecting a lot of dots here faster than I can even catch up. Okay, so, oh, wait a second. Why is there a minus there? That should be a plus. That should be a plus. Why did I put minus? That minus goes through. Sorry about that. Okay, so let's follow through here. So let's look at the x primes. What's attached to x prime? S squared and s. So minus s squared plus s. Okay, what's attached to x? Negative 2s, negative 2s. So that's minus 4s, but what else is there? Negative 1 and positive 1, they cancel. So just minus 4s times x. Oh, sorry, there's a big gap. There's a very big dot. 4s times x. All right, can we clean anything up here? What can we do? What can we do? There seems to be an idea in the back.
Shouldn't you line both sides by negative s squared plus s?
We could. Where are you going with that?
Wouldn't that turn into a linear differential equation?
Well, this is a linear differential equation. There's actually a better name for this. Do you recognize this from the earliest part of the semester? Like the first kind of differential equation we learned. It's like separable. This is a separable differential equation. So, for instance, you can write this as minus s squared plus s x prime equals 4s times x. And then you can move the x across, x prime over x. Move this stuff across, minus 4s over s squared plus s. Now you might be saying, Steve, I thought the point of doing the Laplace transform was to get rid of differential equations, and now we still are doing a differential equation. Have we really gained anything? And we have, right? This was a second order differential equation. Now we're down to first order. So yes, progress. I still claim there's something you can do here. What can you do? Yeah, get some cancellation. Minus 4 over s plus 1. All right. Well, if we're thinking separable, what comes next? Integrate. Okay. X prime over x. What does that become? Is it x? Time to go back and review your course logs. Yeah, it's natural log x. So natural log x. Over on this side? Negative 4 natural log s plus 1. And? Plus c. Okay, so that's natural log of x. So what does that tell us about x? What does it look like? E to the other side, good. E to the other side. The e to the c will be a constant. So what about this? What happens here? The negative 4 goes where? Comes up. S plus 1 to the minus 4. So you can write this as some constant over s plus 1 to the 4th. Minus 4 just means it's downstairs. All right, so good. We've now found x of s. We solved our differential equation. And what we need to do is find x of t. So we pull out our chart for a few moments and say, okay, does this look like anything on our chart? And hopefully the answer is yes. What does it look like? Well, I should say you probably can't see the whole chart because I want to point, we had to start conserving. There's actually two pieces here you should be looking at. What are the two pieces we should be looking at? So notice here we have to a 4th power downstairs. Where do we have like anything to a power downstairs? Like t to the n or t to the n. But there's this s plus 1. That means that we're doing some kind of a shift. What happens if we're doing a shift? That means there's some sort of exponential function multiplying. So really we need to take these two rules together. All right, so if I want to end up, I have s plus 1 to the 4th. Well, that looks like I have, here I'd have 3 plus 1, so n equals 3. So it looks like I'm coming something with about 3 cubed. And then I have a shift over by minus 1. So I'm going to combine those two rules. So first off, let's make it fit this right form here. So now that I took the formula sheet off and so you can't see it anymore, if I have s plus 1 to the 4th, what should I have upstairs? So this is, the constant comes out in front. Think of 4 as 3 plus 1. So n plus 1 downstairs, what goes upstairs? 3 factorial. So in front I would divide by 3 factorial, which is 6. Okay. But of course, what happens to this c over 6? Becomes c again, right? Because your constants can absorb constants. It's one of those cool things. And you can go home and show your family, like, look at this cool thing. And they're going to be like, what? What happened to the over 6? Constants can absorb constants. And you're like, wow, that's so cool. All this cool math you're learning. All right, we're almost there. What does this become? Well, it should become t cubed. But because of our shift, right, that would, if we just had 3 factorial over s to the 3 plus 1, it would be t cubed. But when we have a shift, we multiply by an extra piece. So what do I need to multiply this by? E to the minus t. And so that's the other function. All right. Good. Now, I should note, there was an instruction, find a non-zero solution. Good news is that's not zero. You might ask, well, why did they specify a non-zero solution? Well, is there another solution to this where x of 0 equals 0? Yeah. What's the other solution? 0. Yeah, not an interesting solution. So it's just trying to say, find an interesting solution. Okay, well, let's try this one. Okay, but we're going to have to go quick. Find the Laplace transform of sine of t over t. This one's going to be great. Okay, so if you think back to the table, what does this remind you of? What can we connect to? So which one are you thinking about? Well, t sine t is multiplying by t. We want to divide by t. But what are we close to? So I want to point here. Let's start with sine. And you're probably thinking, that's a weird place to start, but okay, we'll start there. The Laplace transform of sine of t. All right, that is, I'm just copying it from the sheet here, 1 over s squared plus 1. Okay, let's give this a name. The Laplace transform of sine t over t. Let's call this, we already have a name, f of s. Okay, we don't need to give it a name. Great. All right, so here we go. This is the fun part. So the Laplace transform of sine of t is 1 over s squared plus 1. Now, that is the same as the Laplace transform, and check this out, t times sine of t over t. Now, why is that? The t's cancel. Yeah. Multiply t, divide by t. Yeah. You haven't done anything, Steve. Yeah, exactly. Good. All right. But according to our rules, if I have t times something, what does that correspond with? It's negative this derivative. All right. So f prime of s is negative 1 over s squared plus 1. Okay. Do we know an antiderivative of 1 over s squared plus 1? Arctangent. And you're like, oh, no wonder Steve wanted to do this problem. Typical Steve has to get arctangent in there somewhere in the semester. Am I missing anything? Plus C. All right, now this is not the punchline that there's arctangent. There's the punchlines coming up. This is cool. All right, we've got ourselves a plus C. How do we find the right choice for C? It's a great question. Oh, there's a recall here. Okay. Our functions should go to 0 as time goes to infinity. Now, currently, what happens to arctangent as s goes to infinity? What does this do? Do you remember the arctangent function? So if you think about the tangent function, it looks like this. Where are the asymptotes at? Pi over 2, negative pi over 2. And then what to do is to get to arctangent is you pick it up and you flip it over. There's that flipping across the line y equals x. So your vertical asymptotes become horizontal asymptotes. And so that's what arctangent looks like. So as time goes to infinity, arctangent goes to pi over 2. So what does C need to be for this to work? So we have negative pi over 2 already. So we need to have C be pi over 2. So f of s is pi over 2 minus arctangent of s. All right, good. But I said that's not the punchline. Here we go. What is f of s? Well, it's the integral 0 to infinity e to the minus st times the function sine of t over t dt. And we know what f of s is. We just computed it. What is f of 0? Well, plug 0 here. What do you get?
0.
Arctangent of 0 is 0. Pi over 2. What happens when you plug 0 here? The e to the minus st becomes 1. So pi over 2 is equal to the integral from 0 to infinity of sine of t over t dt. That's true. That's actually true. And that's cool, right? Like, wow. This is like stuff you can go home at Thanksgiving and share with your family. You'll never believe it. This is a totally cool fact. Remember last year when we were talking about calculus and we talked about sine t over t? I'm going to top last year. If you integrate that function from 0 to infinity, it's pi over 2. What? Amazing, amazing. Okay, great dinner conversation. You know, if the turkey doesn't put him to sleep, this will. All right. So, last idea for today. We're going to talk about something called convolution. And it's this weird idea that it's kind of acting like a multiplication. But what is it? Well, the convolution of two functions, f of t and g of t, we have this notation. It's f star g. And it's defined in the following way. So f star g of t is the integral from 0 to t f of tau g of t minus tau d tau. Now, what's going on? This is not the best example, but unfortunately, this would be better with animation, but I can't do animation, so I can draw. And let's do like a very simple example. Suppose I was doing t and t. So f and g are both t. So when I think about f of tau, well, that's just a normal function t. So we know what that looks like. When I think of g of t minus tau, well, what I've really done is I'm running the function backwards. That's the minus tau part, and I've shifted the function over. So if I'm looking at 2, I would shift to 2 and run backwards. So one part runs forward, the other part is shifted running backwards. And then you multiply them, so you get a curve. So this curve is the curve f of tau, g of t minus tau. And now you look at the area underneath that curve, and that area is f star g of t. And you're like, okay, great. So that's what the convolution is. That's just a definition. Now, what can we do with it? Well, it's a fact. F star g is g star f. Okay, so it doesn't matter which order you go. In essence, what happens is if you compare f star g versus g star f, is you just flip the picture. But if you flip the picture, you don't change the area. So, yeah, f star g equals g star f. Let's do a really quick example. T squared star t cubed. Now, because we can flip, this is the same as t cubed star t squared. So, and I do want to be really quick here, because the punchline is convolution is this weird way of multiplying. This is how you should think of it. Is you're multiplying the two functions to produce a new function, but it's the right way to multiply when it comes to the transform here. All right, so here we go. By the definition, 0 to t, then we're going to do our f will be t cubed, so it'll be tau cubed. And then the g will be t squared, so that'll become t minus tau squared, d tau. All right, if you had to do this integral what would you do? What?
FOIL the inside.
Okay. FOIL, expand. So t minus tau squared, well, t squared, so that we get a tau cubed t squared. Then there's a minus 2 times t times tau. Don't forget that there's still a tau there. So it'll be minus 2t tau to the fourth. Then there'll be a tau squared and a tau cubed, tau to the fifth, d tau. So expand out. All right, now we're integrating with respect to tau. T's are constants. Tau's are what changes. So what's the integral of the first piece? Well, the t squared stays as t squared. 1/4 tau to the fourth. T squared. The next piece? 2 over 5. T tau to the fifth. The last piece? 1/6 tau to the 6. Evaluate from 0 to t. When you plug in 0, what happens? 0. When you plug in t, you get 1/4 t to the fourth t squared, which is t to the 6. 2/5 t to the fifth, that's t to the 6. And 1/6 t to the 6. Now, if you get a common denominator would be 60. 4, 5, and 6 all divide into 60. You'd have 15 over 60 from the first piece. Here you'd have minus 24 over 60 from the second piece. And here you'd have 10 over 60 from the last piece. And if you can keep those three numbers in your head, 15 minus 24 plus 10, put it all together, 1. So that is the answer, 1/60th t to the 6. So that's the convolution of t squared and t cubed. Now, why do we care? We care because it's exactly the right kind of thing we need to handle multiplication. So we're going to let f of s be the outcome of taking the Laplace transform of little f, g of s the outcome of doing the Laplace transform of little g. And we're going to look at the multiplication. So there's a couple of steps here. The first step is to say, well, definitions. And these are the definitions of the Laplace transform. The only thing that's different than usual is we've changed our symbols on the inside. Normally we use t's. In the first one we changed to x's. If I replace the t's by x's, what happens? Nothing. I just write x's instead of t's. Same thing here, but now I use y's. And now we're going to take these two integrals and we push them together. So there's an integral 0 to infinity, integral 0 to infinity, dx dy at the end. Well, we grab the pieces, the f of x, the g of y. And now you have two exponentials and you can put them together. E to the minus s times x plus y. All right, so far, no surprises. Then comes this step. The dot means this is the interesting step. Let's just accept it for a second. We'll explain why. Because integral 0 to infinity, integral 0 to t. And what happens here is we say, we want this to look like a transform. So we're going to make x plus y into t. That's the key here. And the way we do it is we're going to let x become tau, and y becomes t minus tau. And if you can check, x plus y, if you add those together, what do you get? T minus tau plus tau is t. All right, and now the last thing to do is to say, oh, this e to the minus st can come out of the inner integral because it doesn't depend on tau, and you have this inside integral, 0 to tau, f tau g of t minus tau d tau is the convolution. So the only question is, why did this work? And here's the picture. Give me one more minute. If you think about this integral, we're saying integrate where x goes 0 to infinity, y goes 0 to infinity. So we're integrating up here. And so the way we integrate it is we slice it. That's what's happening. And now we say, well, we're going to integrate the same region. We're not going to add anything. We're not going to remove anything. But we're going to change the way we slice. And the key is to say, I want to slice where x plus y is constant. So that says we're going to slice at angles. So x plus y equals constant t. So we're just changing the way we slice the integral. We still have the total pieces. Everything's still accounted for. We just change the way we slice. This is sort of a little bit of flavor of Calc 3. And for all those Calc 3 nerds who might be saying, what about the Jacobian? It's 1. So we're good. So that's what happened. That's the geometry behind it. Next time, some examples. And have a great day.